press the bell icon on the YouTube app and never miss another update.
Today we are discussing part 8 of the chapter Oscillation. In the previous class we have discussed about force constant and oscillation of a loaded spring. Now, by which we have also derived an expression for oscillation of in period of oscillation of a simple pendulum. Now, let us discuss some important points regarding the period of oscillation of a loaded spring. Now we have period of oscillation of a loaded spring. Right. Now that T comes out to be equal to 2 pi into square root of m by k, that we have shown while discussing about force constant k. Later we have derived this expression 2 pi into square root of L by g. This is the expression for time period in terms of mass and force constant and in terms of increasing length of the spring and g. Remember that we have shown this k is equal to mg by L when a spring is loaded with a mass m, then the force acting on the spring is mg, and that is in magnitude equal to the restoring force. The extension or increase in length due to the application of force is L. Therefore, k is equal to mg by L. Here we have substituted the same thing to obtain this equation. Now, from this expression, so period of oscillation of a loaded spring is directly proportional to mass of the spring. That means P increases with increase in mass of the suspended body. So here P is directly proportional to square root of m, means if the value of m is increased by n times, then the T increases by square root of n times. Suppose if we double the mass, then the T value increases by root 2. Suppose if we increase the mass by 4 times, then T increases by square root of 4, that is equal to 2 times. If we are having the two masses for the same spring, m1 and m2 are suspended, then T1 and T2 are obtained, then we can write T1 by T2 is equal to square root of m1 by m2. Now the second one, so T is inversely proportional to square root of force constant from this equation, since 2 pi is constant. That means to say, higher the value of k, smaller is the time period. Smaller the value of k, higher is the time period. That means so for stronger spring, time period is less. For weaker spring, time period is more. Now T is more for weaker spring than a stronger spring, right? That means if the value of K, that we have F is equal to Ky, right? If the value of K is very high, then a large force can produce very small, right, displacement. That means spring is strong. If the value of K is less, then even very small force can produce a large displacement, that is a weak spring, right? Now the third one, we have this T is directly proportional to square root of length, right? Now that means where L is the increased length of the spring when load is attached, right? So T increases with increase in length of the loaded spring, right? Now this is how time period depends upon mass K and L, and of course here acceleration due to gravity G is constant at a given place. Its value will be changed only if we change the place. That usually won't happens generally, right? At a given place G is constant. Now the fourth one, this relation T is equal to 2 pi into square root of, right, M by K, right? It holds good for a loaded spring, right, oscillating in horizontal direction. This is M. Now oscillating in horizontal direction. This is the spring constant K. Then the time period T is equal to, right, 2 pi into square root of M by K, right? So you have to remember these things, right? They will help you in answering understanding based question, application based question, skill based question, solving numerical problems in competitive examination. Okay. Now let us take another note, say note 2 here, right? Here we will take, right, A, right, when a spring is connected to two masses. When a spring is connected to two masses, so number one, we will take that this is a horizontal plane. Now a mass is M1 is placed on the horizontal plane. Now we put another mass M2, right, so that a spring connects both M1 and M2. Here this is the value of K, right? Now here generally when we the mass M2 began to oscillate, right? Here generally M1 won't oscillate, M2 only oscillates. So when M2 alone is oscillating, right, then the time period T is equal to 2 pi into square root of m2 by k, where here m2 is the mass of the oscillating body. In this case, m1 won't oscillate. Now the second case we take here, this is a horizontal plane. Now we have a spring of spring constant K. Now one end of the spring is attached to a mass m1 and the other end of the spring attached to another mass m, right? Both are compressed. The both masses m1 and m2 began to oscillate in right horizontal direction, right? Both masses are oscillating here. Here only one mass m2 is oscillating. Suppose if t is the time period here, we see when only one mass is oscillating, t is equal to 2 pi into square root of m by k. Now the two masses are oscillating, right? So here when both m1 and m2 are oscillating, then what is the value of m there? That is called as, now we have to consider the effective mass of the two bodies. The effective mass is not just m1 plus m2 here. Here the effective mass of the system me is equal to m1 m2 by m1 plus m2. Through the mathematical steps and derivation, right, we can show that the effective mass of the system of two masses attached to a string, right, is me is equal to m1 m2 by m1 plus m2. Now the period of oscillation, right, t is equal to 2 pi into square root of me by k, or t is equal to 2 pi into square root of m1 m2 divided by k into plus m2, right? Now this is how we can obtain the period of oscillation when a spring is attached to two masses, right? In the first case only one mass is oscillating, but in the case 2 both the masses m1 and m2 are oscillating. Remember here the effective mass changes. Effective mass of the system is, right, m1 m2 by m1 plus m2. Is that clear? Now we will take P of combination of springs. Now period of oscillation of combination of springs. For example, in a jetter pen we use only one spring, right? When we observe practical application, for many practical applications we have to use more than one spring. When more than one springs are used, then it is called as a combination of springs. You see the springs which are used in motorcycles of, right, the shock absorber, right, they are like that. This is one spring on left side, this is another spring on the right side, right? They have connected at a point, right? Now we can also have a spring, one spring and another spring arranged like this, right? K1, this is K2, say this is of K1 and this is of K2. So in this is called combination of springs. Springs can be combined either in parallel combination having same common point, right? Now they can be arranged in series one by one, right? So this is parallel combination and this is right series combination. Now what is the change here? In general, for any loaded spring, T is equal to 2 pi into square root of M by K. When a mass M is attached to this one, but here, since we are using more than one spring, the effective value of K has to be taken. What is the total value of K1 and K2? What is the total value of K1 and K2 here? It is not just K1 plus K2. It may be in some case K is equal to K1 plus K2. But it is not in the other case, right? It may be different. That depends upon how the spring reacted to the external applied forces, right? This is parallel combination and this is series combination. So in many practical applications, we are using more than one spring with series combination or parallel combination, right? We will take A, right? Springs connected in series. Springs connected in series. Now let us consider two springs. This is of force constant K1, this is of force constant K2. So when we apply a mass, mean weight, by attaching a mass, weight mg is acting vertically downwards, that is the displacing force. So there is an extension or displacement in both the springs here, right? But the force on each spring is same here. So here also the force F equal to mg. Here also it is the force F equal to mg, right? So in this case both force, right, the restoring force on the spring or developed in the spring is same. So in this combination, that is in series combination, in series combination of springs, right, restoring force F is same on each spring, right, restoring force. But we know that F is equal, I am only taking the magnitude, neglecting the negative sign. So K1 Y1 is equal to K2 Y2, where since K1 and K2 are two different values, right, now therefore Y1 and Y2 are different, right? The displacement here it is Y1 and displacement here it is Y2. That means here and, right, extension of each spring is different, that is y1 and y2. So again here mass is the same, there is no change in mass is only one, that is m suspended, but we have to take effective value of, right, force constant. Here effective force constant, right, that I will take Ke, sometimes we can take Ks indicating it is a series combination, that comes out to be 1 by Ke is equal to 1 by K1 plus 1 by K2. Remember that, where Ke is the effective value of force constant. So, or Ke is equal to, taking the LCM and reciprocal, K1 K2 by K1 plus K2. Therefore, now the period of oscillation, now the T is equal to 2 pi into square root of m by Ke, right, where what is Ke? Effective, right, force constant, or T is equal to 2 pi into square root of m into, substituting that value here, this is K1 plus K2 divided by K1, right. This is the time period of oscillation when the springs are connected in series. Is that clear? Right. Now, right, if n springs of different force constant are in series, just like this is K1, K2, K3, etc. Kn. This is K1, K2, K3, etc. Kn. Then in this case the effective, right, force constant is 1 by Ke is equal to 1 by K1 plus 1 by K2 plus 1 by K3 plus etc. and time period T is equal to 2 pi into square root of m by K. Generally when we take for two systems, so here we have this Ke is equal to K1 K2 by K1 plus K2. Suppose if we put K1 is equal to 1 and K2 is equal to 10. See, Ke is equal to, this is 1 into 10 by 1 plus 10, that is 10 by 11, it is less than 1. Suppose if K1 is 1 Newton per and K is 10 Newton per meter, but the effective value comes out to be less than 1. That is, the Ke is less than K1 and also Ke is less than K2. So the effective is always less than the least of a force constant, right? So if we use individually, right, this has a period T1, this has a period T2 separately, as a single spring, but when they are used in combination, the effective value of K decreases, right? Now that means, right, in series combination, in series combination, right, effective K, that is KE, decreases. Is less than K1 and less than K1. Therefore, period of oscillation is more. That means if T1 is period for single spring K1 and T2 is period for single spring K2, then the value of T of combination is less, more than T1 and more than T2, because it is inversely proportional to the force constant. As the force constant decreases, period increases. So, series combination of spring, right, force on each spring is same, right. Now displacement of each is different, I mean extension is different. The value for two springs, right, 1 by K is equal to 1 by K1 plus 1 by K2. Springs 1 by K is equal to 1 by K1 plus 1 by K2 plus 1 by K3, etc. The period of oscillation of a series combination of spring is more than the period of oscillation of a single spring of the combination. Is that clear? B, right, parallel of springs. Let support. Now we have two springs. To the same rigid plate here. This has K1, this has K2. Now the two springs, lower end of two springs are connected to M. When M is attached at the lower end, now the force mg is a restoring force is developed on the spring. So here in both the cases the displacement is same, right? The displacement is same. Here we have F1 is equal to K1 Y1, F2 is equal to K2 Y2, right? Sorry, because displacement. Therefore, for each spring is different. This is F1, right? Restore F. That means in parallel of springs, right? Force on each spring is different, but the extension or displacement produced by each spring right. On is and is same for both springs. That is why, remember, in series combination force is same, F extensions are different, y1 and y2. In parallel combination forces are different, they produce the same extension here, right? That is now in this case effect force constant K2, right? Force constant Ke is equal to K1 plus K2. Therefore, period of oscillation T is equal to 2 pi by square root of m by Ke, or T is equal to 2 pi into square root of m by K1 plus K2, right? Now, if K1 is equal to K2, we have the value of K2, then the time period T is equal to 2 pi into square root of m by 2 K1 or 2. This is when the two springs have same spring constant, right? And now for so K1, K2, right? Mg mass attached, right? Then here the effective value of force constant is equal to K1 plus K2 plus K3 plus etc. plus it is Kn, and period T is equal, right, equal to K plus etc. plus Kn, right? The period of oscillation. Now let us compare the period parallel combination. Here obviously we see that when we take two springs, Ke is equal to K1 plus K2. this KE is greater than K1 and KE is greater than K2. In parallel combination, so effective KE, right, increases, K value decreases. Remember, in series combination, effective force constant decreases, but in parallel combination it increases, right? Square root of KE. Now the period of oscillation is less. Suppose it period of oscillation for single is a period of oscillation for single spring, then E1, right? So series combination, the effective value of, right, force constant decreases. Period of oscillation. In parallel combination, the effective force constant increases, but the period of oscillation decreases. We will special case. We have a of constant K1 to a mass M, and we added another spring of K2, and it is also connected to a rigid support, right? Now the mass, it stretches the spring K1, but it compresses the spring K2. Suppose if it, the load, there is same for this class, right? But the restore, so here in this case it is same, but the restoring forces are different, right? So two effective force constant that is equal to 2 K2 compared with the period of individual springs, right? The effective value of force constant increases and the period is less. So this arrangement is equivalent to two springs connected in. Now the summation of storing forces displayed what force constant, effective value of force constant, right, in the two cases, as well as how period changes. Of course, what we have discussed so far in this full, right, in, right, solving the problems, especially in competitive examinations, right? Okay. Right. We will take another explanation of a simple here we will derive an expression for, right, period of oscillation of a simple pendulum. A simple pendulum consists of a spherical metallic bob, right, suspended by means of a light inextensible string, not spring, right. So it is light inextensible string, string. String means it is thread, rope, any wire, right, is called as a string. It is a light means almost its mass or weight is negligibly small compared to mass and weight of the bob. So inextensible string means, right, generally when a string is stretched, slightly there is an increase in the length, but here under the weight of that bob there is no extension in the string, right. So clearly a simple pendulum consists of a metallic bob, right, suspended by means of a light inextensible string, right. Now let us here now let us consider a simple pendulum. Right. 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 Now let us consider a simple pendulum of bob of mass m attached to, right, a light inextensible string of length L. I will take it position O. Right, generally the length of a simple pendulum is not just equal to the length of the string, but in fact the length of the pendulum is the distance between the point of suspension to the center of mass or center of gravity of the bob where its mass is used to be, right, concentrated, right. Why we are taking spherical bob? Because it is easy to locate the center of gravity and accurately measure the length of the simple pendulum. If it is an irregular body, okay, it acts as a simple pendulum with certain period of oscillation, but it is somewhat complicated to locate that center of gravity so that we cannot find the exact length of the pendulum, right? Now, let PO be mean position of a simple pendulum. It is the mean position. Now, let us displace this bob through a certain distance d. Now, the bob has displaced to the position A, displacing through a horizontal displacement x. Here I am taking x, where generally in case of spring we have taken the displacement y. Here I can take it is x because it is a horizontal displacement. Now the string, right, displaces through an angular displacement theta. At any interval of time, let A be the displaced, right, position of the bob, right. Now let A be displaced position of bob at any instant of time t. Now at A we have linear displacement, right. OA is equal to x and angular displacement, right, angle OPA is equal to theta, right. Now also we have arc length is equal to, right, L into theta, or theta is equal to x by L. From figure, this theta is equal to x by L, or x is equal to theta into L. Arc length of a circle is equal to, right, the angle subtended at the center of the circle into radius. From that concept, theta is equal to x by L. Now at this position, right, the two forces acting on the bob are, right, weight of the bob acting vertically downwards and tension in the string along the direction AP. Now forces on bob at A. Number one, tension in string P along AP as indicated by the arrow mark. Number two, weight of bob mg vertically in downward direction. Now here we can use the concept of resolution of a vector. Resolution of a vector like displacement, velocity, acceleration, momentum, force, electric field, magnetic field, etc. is the process of finding the magnitude of a given vector in any number of desired direction, right. Here, right, this mg can be resolved into two mutually perpendicular components. They can be resolved into two mutually perpendicular components, right? See it here. Right. This mg can be resolved into two mutually perpendicular component with this angle theta, because this angle is theta, and the component is, this is mg cos theta, and this component is mg sin theta. Right here, this mg cos theta balances the tension. Here component mg cos theta balances tension P, right, and unbalanced component mg sin theta provides the restoring force to bring the bob back to mean position. Mean position P, right. You see it here. As long as I hold it, the bob at this position, right, now there is, the bob is at rest under the action of three forces: tension, mg and my force. When I withdraw that force by leaving the bob, now these two forces are balanced forces, P and M. Therefore, the bob will not move either along OP or along PA. There is no component towards positive x direction. There is only one component, that is the force, right? That is the magnitude of the weight in the negative x direction, say, right? Along this direction, just I have taken towards left, I can take. Is mg sin theta, it is not at all balanced. Hold that mg sin theta is balanced by, right, the displacement force. When I leave that, this becomes unbalanced and that tries to move the bob to its mean position. Is it correct? Right. Now let us derive expression for time period. Now the restoring force on the bob, right, F is equal to minus mg sin theta, because the negative sign indicates that the force is always directed towards the mean position PO, right? That is the significance of this negative sign. But since theta is very small, we have taken the value of angular displacement is very small, then sin theta is nearly equal to theta. This is the concept of trigonometry. When angle theta is very, very small, then sin theta is nearly equal to theta, and of course tan theta is also nearly equal to theta. Therefore, we have restoring force, right, F is equal to minus mg into theta, right. Now, so when the force is acting on the bob, that produces an acceleration towards the mean position. Now the acceleration of bob, right, directed towards the mean position. A is equal to F by M. That is F by M. That is equal to, right, minus mg theta by M. Therefore, right, acceleration A is equal to theta. From figure, right, by L, right, therefore we will take equation like that. Therefore, acceleration A is equal to minus g into theta, that is x by L. Now I will take this as equation 1. Now this body is executing, acceleration is directly proportional to displacement, and it is direct. Now acceleration of simple harmonic motion of ball, right, A is equal to minus omega square x, equation 2. While discussing minus square displacement, here x is the displacement. Again, negative sign indicates that the acceleration is directed towards the position. Now from equations 1 and 2, minus so here negative sign get cancelled. Now we have omega square is equal to g by L, or omega is equal to square root of g by L. But what is omega? 2 pi by t is equal to, right, square root of g by L, or right, equating that one, right, t is equal to 2 pi into square root of L by g. This is the expression of T is equal to square root of 2 pi into L by g, where L is a simple pendulum, that is the distance between the point of suspension to the center of gravity, right. So that includes the length of the spring from P to the surface of the spherical bob plus radius of the bob, that is equal to the length of the simple pendulum. It is not just the length of the string by which the bob is suspended. It is the distance between point of suspension to center of gravity of the bob, right. Is that clear? Now again, we obtain the same expression for oscillation of loaded spring. T is equal to 2 pi into square root of L by g, but where L is the, right, increase in length of the spring when mass m is attached to the spring. But here L is the length of the simple pendulum, that is the difference. Again, g is acceleration due to gravity, right. Now let us conclude this class, right. Remember that in this class we have discussed, right, different cases of right, period of oscillation of springs with one mass, with two mass, series combination, parallel combination, special case, etc. Basically remember that one, in combination of spring, what happens to force? what happens to displacement, what happens to effective force constant, and what happens to the period of oscillation of combination of springs. And this derivation is usually asked, right, in board examination for 5 marks. It is a 5 marks derivation, very important, right. This question often appears in the first PUC board examination, right. Okay, thank you very much. Let us continue in the next class, that is part 9.